With fraction addition, addition, subtraction of fractions, we do need to recognize whether we have like terms or not, because I can only add like terms. 3/8 plus 7/8, can think of the eighths as my units. I have 3 apples plus 7 apples, so I have 10 apples. I have 10 eighths. These are like terms, so I can add them. Now, I have to be sure my answer is reduced. This is where the prime factorization can come in. 10 is 2 times 5. 8 is 2 times 4. 4 is 2 and 2. I've got a common factor of 2. So this simplifies to 5 over 4. And that's reduced. If I had 11 twelfths plus 3 twentieths, I've got a problem here. 11 apples plus 3 oranges. I have unlike terms. I'm not able to add these fractions unless I have them with the same denominator, unless I have like terms. Now, what I'm going to show you for the fraction addition here is going to feel very strange. So bear with me. You might want to just watch this example once, then rewind and watch it again with trying to understand what's going on. So what I'm going to do is I'm going to factor both denominators with the prime factorization. 12 is 4 times 3, so 2 times 2 times 3. And I can use a factor tree off to the side if I need it. 20 is 4 times 5, 2 times 2 times 5. So the first thing I'm doing is finding the prime factorization of the denominators. And by the fundamental theorem of arithmetic, we know that prime factorization is unique. Now, to have like terms, I need to have the same units. I need the denominators to be exactly the same. Well, I'm going to look at both denominators and I'm going to look at the factors. And I'm going to say, well, this denominator has a 2, a 2, and a 3. This one has a 2, a 2, I've got both of those, and a 5. I don't have the 5. So I'm going to put the 5 in over here. I'm going to multiply by 5. But I have to be careful not to change that fraction. I can only multiply by 1, so I have to do the same thing in the numerator. Multiply by 5 over 5, I've multiplied by 1, I haven't changed that number at all. I've just written an equivalent number. Over here, 20, 2 times 2 times 5. 2 times 2, 2 times 2, I've got it. 5, got it. 3, don't have. Put in a 3. To avoid changing the fraction, I multiplied by 3 in the denominator. I have to multiply by 3 in the numerator, so I'm multiplying by 1. This is why I like using another color to show what I'm doing with addition, subtraction, anytime I'm changing the problem a bit, being careful that I can see that I'm multiplying by 1 here. If I only had a 5 in the denominator and not in the numerator, I'd hopefully recognize, and you see that a lot better if you're using color. So, I'm going to multiply by 1. Putting in those missing factors. I'll say. So that the denominators have the same factors. And so this is a way that you can find the least common denominator. It can be written out in terms of prime factorization. The advantage of this technique, this method, is that this is exactly how we're going to be doing addition and subtraction of rational expressions, where our numerator and denominator are polynomials. You could not just count multiples of 12 and multiples of 20. if you've got just 12 and 20, you can count multiples of 12, multiples of 20, and find the least common multiple. You're not going to be able to do that if your denominator here is x squared plus 3x plus 5, and here x squared plus 2x minus 7. You're going to have to do the factorization. So 5 times 11 is 55. 55 what? Well, I don't really care what that denominator is. It's 2235. 2235, whatever that number may be. Plus 3 times 3 is 9 over 2235. 2235. I have the same denominator. I have 55 apples. I have 9 apples. Altogether, I have 64 apples. 2235. Those are my units. Now, what is the benefit of leaving that denominator factored rather than multiplying it all together? Well, at the end, I haven't spent time doing that multiplication if I don't have access to a calculator. And to see that this is reduced, I need to find common factors with the numerator and denominator. Well, 64, 8 and 8. 8 is 2 and 4. 4 is 2 and 2. 2, 4, 2, 2. So 64, 2 to the 6th power. In the denominator, 2, 2, 3, 5. I can see then that there was a common factor of 4. I can divide out both of those 2's, and I am left with an answer then of 2 to the 4th, which is 16, over 3 times 5, 15. So 11 twentieths plus 3 twentieths is 16 fifteenths. And again, the work we did within there, we wanted to have the same denominator, so we had like terms. We factored both denominators. We put in missing factors so that we could have the same denominator. We could have apples and apples. I can't change that number, so I can only multiply by 1. So be very careful that you do the same thing to the numerator as you do to the denominator. Again, 3 over 3 is 1. 5 over 5 is 1. We're multiplying by 1. When I have the common denominators, I'm able to add the numerators. Then I just need to be sure that my answer is simplified. This is how you add fractions or subtract fractions. Let's try another one. Eight 15ths minus 13 90ths. So you can try this on your own and pause the video and then come back at any point. So I'm trying to subtract 2 fractions. To subtract 2 fractions, well, to subtract anything, I need to have like terms. Right now I don't. I've got 15ths and 90ths. They aren't like. So what I'm going to do is I'm going to find the prime factorization of each denominator. I don't care about the numerator. That's just how many I have. 15 is 3 times 5. 90 is 9 times 10. Well, 9 is 3 times 3. 10 is 2 times 5. Again, you can always do a factor tree off to the side to be sure that you have you haven't left anything out. I wouldn't recommend doing that mentally until you're really comfortable with it. Well, a 3, a 5, a 3, a 5. This one's missing a 2 and a 3. See the 3, 3, 5, 5. This 2 I don't have here. I need to put it in. This 3 I don't have here. I need to put it in. I've multiplied by 6 on the denominator. To avoid changing the fraction so that I'm writing an equivalent fraction, I need to multiply by the exact same thing on the numerator. Over here, 2, 3, 3, 5. 2, 3, 3, 5. I now have like terms. So my numerator on the first one, 2 times 3 is 6. 6 times 8 is 48. I have 48 apples. 2, 3, 3, 5. Minus 13 apples. 2, 3, 3, 5. The same denominator. 48 minus 13 is 35. 35 what? 35 apples. 2, 3, 3, 5. Now, to be sure that I reduce my answer, 35 is 5 times 7, prime factorization. And look at that, there was a 5 in common. This simplifies to 7 over 2 times 3, 6, 6 times 3, 18. So 8/15 minus 13/90 is 7/18. Again, by using the prime factorization, we're able to always find the least common denominator relatively quickly, and it makes reducing the fraction a lot easier at the end of the arithmetic. Let's do one more. 10/21 minus 3/70. So 10 over 21 minus 3 over 70. Pause the video, try this on your own. So, to add fractions, I need to have like terms. I need to have the same denominator. 21 is 3 times 7. 70 is 7 times 10. 10 is 2 times 5. So, the first fraction is missing a 2 and a 5. So I need to put in a 2 and a 5. What I do to the denominator, I have to do to the numerator so that I can multiply by 1 and not actually change my fraction. 2, 5, 7, I'm missing a 3. Put the 3 in the denominator, put the 3 in the numerator. 2 times 5 is 10, 10 times 10, 100. 100 what? 100 apples. 2, 3, 5, 7. Minus 3 times 3, 9, over 2, 3, 5, 7. I've got the same denominator. I've got 100 apples minus 9 apples. I have 91 apples. 2, 3, 5, 7. Now, the question is, can this be reduced? Well, a fraction can be reduced if there's a common factor between the numerator and denominator. This is again another one of those places where the prime factorization is extremely useful. Does 2 divide into 91? No, 91 is odd. If it were even, 2 would be a factor of it. Does 3 divide into 91? Well, the sum of the digits for 91 is 9 plus 1, 10. 3 doesn't divide 10, so 3 doesn't divide 91. Divisibility test for 3. Does 5 divide into 91? No. 5 will be a factor if the last digit is a 0 or a 5. So the only number I need to check to see if this is reduced is 7. If 7 divides into 91, then I can divide out that common factor. If 7 doesn't divide into 91, then I don't care if 91 factors in any other ways because I don't have any of those other numbers in my denominator. So scratch work to the side, I just need to check. Does 7 divide evenly into 91? And it does. 91 factors as 7 times 13. And that's not going to be the sort of factorization you just see automatically like you have with all the others. 7 is the common factor, we can divide it out. 13 over 2 times 3, 6, 6 times 5, 30. And I know this is reduced because I've used my prime factorization.